Welcome everyone for this webinar series. Today we have the great pleasure to welcome Professor Sir John Pendry from Imperial College. And John is going to talk about localization of light in ordered time-modulated media. Professor Pendry.
Thank you, Sebastian. I'm going to share my screen now and fire up my book. Time-dependent systems are the next stage in metamaterials. Metamaterials, of course, have generated an extraordinary set of properties that weren't available previously in electromagnetism. But also they're important in acoustics, which is particularly relevant to this audience, which is focused on acoustics, I guess. And many of the things I say today will perhaps even best be realized in acoustic systems. The model I'm going to take for time-dependent systems is of a moving grating in which epsilon and mu are both modulated, but the modulation progresses through the medium. Now, it's important to mention here that I'm not suggesting that the medium itself moves. The medium is stationary. It's just that the modulation is phased in such a way that it appears to move. Because the medium doesn't move, there is no restriction of the velocity with which the grating can move. It can move as fast as light, and it can move faster than light, and it can move infinitely fast as well. And that extraordinary range of velocities is going to produce some very interesting effects, including the localization, which is the title of my talk. And another thing where the absence of material motion is important is in experimental realization, because obviously if you were talking about experiments in which you move a material almost as fast as light, then that wouldn't be a sensible experiment. But it's perfectly sensible to conceive of a system in which you modulate the system with a velocity approaching the speed of light. And there are instances of that, which I'll mention if I have time. So those are the sort of systems we're concerned with. And there are several regimes. The one which we're going to be interested in, which we'll come to in a moment, is when the velocity of the grating is of the same order as the velocity of light in the system. And there are two critical velocities, a lower one and an upper one. And within those, you get this localization effect that I'm going to talk about. Before then, I'm going to talk about gratings which are moving either much less or much greater than the velocity of light. And under those circumstances, the system is delocalized. The system is PT symmetric, and it supports block waves with band gaps, either in frequency or in wave vector. Here is a dispersion relationship. On the left, you see the dispersion relationship of light in a uniform medium, a dielectric or vacuum, whatever. And I've given the dispersion two colors there. When the frequency is positive, then I color the lines red. And when it's negative, which represents negative refraction and negative frequencies, then I color them cyan. Now, in a normal grating, that dispersion relationship is displaced by a reciprocal lattice vector G, which you see in figure B. And that causes hybridization between two positive frequencies. And what you're going to see there is a band gap in frequency. And you're very, very familiar with Bragg scattering, I'm sure. But you can also modulate the system periodically in time. And in that instance, something rather different happens. And now you displace those dispersion lines in frequency rather than in wave vector. And you get an overlap between waves which were previously negative frequency and waves which are of positive frequency. And in those circumstances, you get a band gap in K, which is a very different one from a Bragg band gap. There are analogies. So here are the band gaps. And on the left is the traditional photonic. Hello? Is a traditional photonic band gap. And in the band gap, states either decay or grow in space, giving rise sometimes to surface states. On the right is a case where you've hybridized positive and negative frequencies. You're now modulating the system in time, and the band gap that produces has states which decay or grow in. Hello?
我也是，我不知道我这个是通过浏览器，哎，我这个好像不是浏览器，你得把那个弄了。
Can you hear me?
对，你把那个弄下来，但是声音就是特别卡。
Please, people, don't talk during the seminar.
You need to.
Okay. So on the right, we have a system which is modulated in time, and the band gap there is a band gap in which you have states which can grow in time. Energy isn't conserved if you have a time-dependent system, and that's an instance of parametric amplification, where the states, energy is pumped into the states and they grow in time. These situations have been known about for quite a long time. For example, there's a paper as long ago as 1967 by Cassidy in Proceedings of IEEE. You can also have systems which are modulated in both space and time. And I'll give you an example there where we're modulating the dielectric function. And then you have to translate the dispersion relationships both in frequency and in wave vector. And on the left, you see a displacement, which is for a system in which the grating is traveling slower than light. And in that band gap, which is created, you have a conventional band gap with states which grow or decay in space. On the other hand, if you have a superluminal grating traveling faster than light, then you bring into play the cyan curves interaction with the red curves, and that creates this very different band gap where the states are amplified, are growing in time. So that's the big difference between the two cases where you get red on red or red on cyan. If we think of these gratings as metamaterial structures, so that we're sending waves up them with a wavelength much longer than the period of the grating, you can describe them as an effective medium. And something we've done, which I reference here, which is a paper authored by all the talents of Paloma, Emmanuel, Sebastian, and Richard, all of whom are in the audience today. Then if the period is much less than the wavelength, you get a bioanisotropic material with properties analogous to the presence of magnetic field in the case of electronic materials. Now, these materials are impossible or almost impossible to engineer using conventional stationary metamaterials because you in general in optics you don't have that equivalent of a magnetic field. But motion will enable you to get these properties, and this brings us to the famous experiment of Fizeau, in which he confirmed Fresnel's hypothesis that light travels a different speed in a fluid when the fluid is moving. And here's Fresnel's hypothesis realized by Fizeau, in which water circulates around this system here, and then light is sent through two arms and to form an interference pattern. very difficult to experiment. It turns out that Fresnel, although he proposed that this effect was there and got the right formula for it, his reasoning was incorrect. And it took Einstein's theory of special relativity to explain it. And the Fresnel drag is one of the cornerstones of Einstein's special theory. Now, it turns out that to get this effect, you have to modulate both epsilon and mu, as I'll show in a moment. So here we have a medium, which I have a moving modulation, modulated in both electric and magnetic permittivity and permeability. And you can calculate the effect of that. And here is the dispersion relationship of frequency versus the wave vector in the direction of the grating, which is k, and the wave vector perpendicular to that, which is ky. And this quantity delta here, which I'm circling, is the bianisotropic effect, which means that plus and minus k have different frequencies. And the formula we get from that, from our analysis, is shown here. And you can see that it's essential to have both epsilon and mu modulated in order to see this bianisotropic effect. It's almost as if you have to pull along both the electric and magnetic fields together. And if you don't do that, then one won't follow the other. You have to modulate them both to see this effect. And when you've done that, you can see that the dispersion surface here is distorted. And we do, in fact, see an instance of Fresnel drag, even though there is no material motion, it's just the apparent motion of the grating. However, there is a strange twist to this. And in this figure on the right, we see the grating moving to the right, but the Fresnel drag, it turns out, is to the left in the opposite direction. If you modulate the grating with a speed faster than the speed of light, then the Fresnel drag is in the same direction. So that's a little bit of a tour of what happens in a more conventional way with the analogy with dispersion relationships, block waves, and so on and so forth. But now I want to turn to the main theme of my talk, which is this number one situation here, where we move into the critical region. In this region of velocities, the light is localized within a grating period and continuously amplified to form a short pulse. And the block description fails, so there are no block waves available here to talk about. And that happens because of a very curious effect. Now, I've drawn here the dispersion relationships, and I've successively translated them through a reciprocal lattice vector. And because that reciprocal lattice vector is parallel to the positive dispersion, you end up with a series, all the forward scattering waves are now degenerate. And there's an extremely strong interaction between all the forward scattering waves. And this is what leads to the localization and the breakdown. It's strangely enough, you might think that backscattering is the strongest thing that could happen in a grating, but in fact, forward scattering is the key to these effects that I'm going to talk about. Just to give you a peek of what actually happens in this region here, if you have a luminal grating, that is to say a grating which is moving with velocity in these critical regions, and you inject a stream of electromagnetic waves into it, then what comes out of the other end is a series of pulses. The thicker this section of grating, the stronger these pulses are, and the thicker this section of grating, the narrower the pulses are. So this luminal grating has the effect of capturing the light into a series of pulses. The pulses are locked into the same velocity of the grating. It doesn't matter what the velocity of this light here is. They are locked into the velocity of the grating, increasingly localized, and more and more energy. So if you did a spectral analysis of what comes out at the other end, you would have a supercontinuum. But in this, it has a whole mass of different frequencies contained therein. Now, there's something very interesting going on here, because what you can prove is that in the absence of backscattering, the number of lines of force, electrical and or magnetic, the number of lines of force in one period of the grating is conserved. And so if you want to increase the energy of that section of the light, then you have to compress the lines of force. And this effect here is responsible for what we're seeing. So you start with a uniform spacing of the lines of force as the wave enters the grating, and what comes out, the lines of force are increasingly compressed. And by the way, the phase is also conserved and the phase is compressed in the same fashion. This is quite a different way of amplifying radiation from the usual effect where you have gain and a laser, or where you have a parametric amplification process, which is due to backscattering. In those cases, you simply add lines of force to the pulse. In this case, the number of lines of force are conserved, and what you're doing is compressing the lines of force. So that compression effect can be undone. And if you feed the compressed pulse into a grating which is time reversed, then it will decompress the pulse and send out the other side, if it's the right thickness, something which looks like this. So you can time reverse this compression process. Something happened to my screen. Okay. Now what I have here is a simple model for localization. And as I explained to you, the localization comes about because of the degeneracy of all the forward scattering waves, of all the forward traveling waves. And so if we throw away all the backscattering, we end up with a very simple model, which nevertheless shows a localization. Of course, there is still forward scattering, and that's what matters. Now, you can easily eliminate forward scattering in an electromagnetic system by matching the impedance. And you can do this by ensuring that everywhere the permittivity and the permeability are equal. And we will modulate them in tandem like this. And so the impedance will be a constant throughout, and that eliminates all backscattering. And in that case, there are no band gaps. However, the localization persists. Now, one advantage of that is because there's no backscattering, the forward traveling waves and the backscattering waves don't talk to one another. And so Maxwell's equations, which are second order differential equations, factorize into two first order differential equations. And that equation there is a first order differential equation, which we will use to demonstrate localization. Now, that equation is simple enough with this simple modulation of the grating that we can actually find quite a lot of analytic solutions to that equation. If we concentrate on the forward traveling waves, which are described by the minus sign here. These are the ones which interact with the grating, which are traveling in the same direction of the grating. The backward traveling waves are hardly affected at all by the grating. They're slightly affected, but not that. Now, I did say that you can use those equations to solve for the evolution of the wave, and you can use them to write down an expression for the local rate of increase of electromagnetic energy. This is the rate of change of the log of the energy density, which is described by U here. This term here at the end is what you would normally see in the absence of time-dependent modulation. And by the way, I should mention here that we've actually used the Galilean transformation so that I'm working in the frame of the grating. I move, my observers are moving along with the grating. So this is the Poynting vector here, and the Poynting vector is given by the difference between the grating velocity and the local velocity of light, which is CL here, and given by the free space velocity divided by epsilon, which is also the same as mu. But this term here is the one due to the time dependence. And this term is what's going to inject energy into the system. It's going to pump up the energy here. And the function of this term here, which is the Poynting vector and is the flow of energy, this term is going to redistribute the energy. And it's going to be so this term is going to amplify the waves, put energy into the system. And this term here is going to redistribute it. And it turns out the way it redistributes it is to focus the waves into a very sharp pulse. And this term, of course, because epsilon is sinusoidally modulated, can be either positive or negative, depending on what part of the cycle you are. And you only get an increase when this derivative is positive. Let me do that graphically. Here's a plot of epsilon. And again, we're moving along in the frame of the grating. And here, where the derivative with respect to x is positive, you're pumping energy into the system. And the cyan part is where you're taking energy out of the system. Now, the localization is going to occur near something I call an accumulation point. So at this point, the light at this point is traveling at the same speed as the grating. If you move to a region where epsilon is larger, it's going more slowly. And if you move to a region where epsilon is smaller, it's going faster. And so there's a natural flow from either of these sides to this accumulation point. And that's going to be the focusing into a pulse. Now, the rate of change is positive throughout this region. So we're getting energy pumped into the system throughout this curve here. But it's a maximum at this point. And so you get the strongest effect when this accumulation point coincides with the maximum in the derivative. And when the velocity doesn't coincide with that maximum rating, you get a displacement of the pulse which forms. So here is the solution of that equation for those who like, and since I'm talking to a lot of people in the maths department, I'm sure you love equations. Physicists may not like them so much. This term here is the pumping of energy into the system. And it's a maximum when the derivative of this is a maximum. So you get a sine gx here, and that is a maximum at this point here. But the other terms come about from the Poynting vector, and that's the flow of energy around, and they have the effect of sharpening the pulse. So there's an exponential within an exponential. So the pulse, as well as growing exponentially, is actually sharpened exponentially as well. Very, very strong sharpening effect. And here we see what actually happens. And what I'm plotting here is the transmission through a certain thickness d of a grating plotted as a function of time at the exit surface of the grating. So here we don't have a very great thickness of the grating at all. It's 150 units in some units, but nevertheless you still see some amplification and the beginnings of the formation of a pulse. In this case, I've chosen the optimum velocity of the grating, which is equal to the velocity of light, the average velocity of light. Now you make the grating thicker and this process increases. So here the maximum is almost 3 units, and here the maximum goes up to 7 units, but also you see the corresponding compression of the pulse. So this is the pushing together of the lines of force, concentrating them in this region here, near the point of maximum gain and maximum compression. Now, if you don't have the grating velocity equal to the optimal velocity, where the region of accumulation and the maximum gain coincide, but it's offset by this factor delta, then you can see that instead of the gain being a maximum at the maximum input of energy, because of this drift, you see that the pulses form at different points. So if the velocity is, the grating is greater than that of light, then the light lags behind the grating. And so it doesn't come here at maximum gain, a little behind. Or if the grating is moving slower, then the light gets ahead of itself. The red lines are, yes, the black line is computer simulations, essentially an exact calculation. And the red line is the result of our theoretical approximations, which are not very too bad. So what's happening here is that if the light can find a place within the grating where its velocity is the same as the grating, so the light's going slower here and faster here. So as the grating velocity increases, suppose you start off with the grating at the optimum velocity here, and as the grating velocity gets here, the light seeks to localize at a place where the smaller epsilon ensures that it is going faster than ensures that it is going as fast as the grating. But this process can only continue so far. And if the grating is moving too fast, then the light can't keep up with it, and it would need to have an epsilon down here, and that epsilon doesn't exist within all the epsilons available to it, and you get a delocalization, and the light escapes the trap, and we're back into the block wave picture. But that's not the end of the story, because although the light escapes from the grating is moving over it in time. And so as this part of the grating moves over your light pulse, it will get amplified. And as this part of the grating moves over the light pulse, it will get attenuated. So you have this growth and attenuation of the pulse. And the periodicity of that fluctuation will be the difference in between the velocity of the grating and the effective velocity of light. And that will be the period. It will be like a cart moving over a bumpy surface. And I'll give you some calculations which illustrate that point in a moment. Now again, because of the simplicity of that first order differential equation, you can in fact calculate the period of those oscillations when you're in the delocalized regime. So this is a period which is due to the difference in velocity between the average velocity of light and the velocity of grating. And what you see is that period grows increasingly long as we approach this critical velocity here. So delta is the difference between the velocity of the grating and the velocity of light, in essence. And you get a square root singularity here. And this period goes to infinity as the grating moves in to capturing the light from its free localized condition and eventually eats it and localizes it within its confines. And for those of you who are interested in critical transit phenomena and so on, this localization transition is one of the few localization transitions that you can calculate analytically. And in localization theory, the big thing that you're aiming to calculate is the critical exponent. By the way, the critical exponent has never been determined theoretically for localization of electrons in disordered systems. But here, with this localization of light in an ordered system, it's simple enough that you can calculate the critical exponent, and it's an exponent of -1/2. Now, what I'm going to do here is to take you through a sequence of a time sequence. So the time's shown up here. And I start off with some light moving into the system. And here is one period of the grating. So I'm looking at the light as it evolves in this one period of the grating as we go along in time, starting off with its first entrance into the grating. And there, of course, we're injecting a constant stream of radiation. You have a constant amplitude of the radiation. And the first set of calculations I shall show is where the grating is moving faster than the light, and it's moving not only faster than light, it's moving faster than the upper critical velocity. So the light's going to be delocalized, but what we're going to see are these oscillations. So we move one step along, and big surprise, in the gain region, the light gains some amplitude, and the loss region, it loses some amplitude. But because the light is traveling slower than the grating, you can perhaps notice here that it's actually moved off a little bit to the left. And as the process continues, you'll notice this getting more and more. So more and more gain, but the peak is drifting here. And then the peak reaches its maximum at this time here. And now the peak will enter the loss region, and so it will decrease in intensity until finally it comes back and the whole process is repeated. The second set of slides I'm going to show is the case where you have the grating moving slower than the critical velocity. So again, the opposite happens here. So here's the wave which is injected into the system and gain in the gain region. But notice that there's been a motion this time to the right because the light is traveling faster than the grating and therefore it travels to the right. More gain, maximum gain, and the peak now in the loss region comes down and back to where you started. So you see these oscillations. Something you can do is to calculate the effective velocity of the light using that first order differential equation. And you can see that what I've plotted here is, in this case, we're talking about a grating velocity which is greater than the critical velocity. This is the factor by which it's greater than the critical velocity. And when the grating has the critical velocity, then we see that the effective velocity of light is the same as the velocity of grating. And that's just at the point where you're going to capture this pulse and keep it forever in the grating, traveling at the speed of the grating. if you, sorry, this should be less than the lower critical velocity, that should be a minus there. And again, as the grating velocity creeps up to the critical velocity, so the velocity, effective velocity of light, approaches with a square root singularity to that point. And at that point, you again capture the light. And now we enter the region, the critical region, and we start with an electromagnetic wave uniform in space and turn on the grating. But now the grating is capable of capturing the light. And as you move away from this critical velocity, so now this square root is reversed, then instead of getting an oscillatory motion, you get an exponent here, but with the same critical exponent as before, but now this square root is turned imaginary, so you get gain. And I'm going to show you the sequence of so this is the same sort of calculation, but now the grating velocities in the critical region, you'll see quite different behavior. So we start off with a constant amplitude, and as time goes by, the pulse is amplified. It sort of drifts off to the left because the grating is moving a little faster than the velocity of light, but eventually it finds the position where it's going to be captured and localized. And and that's where it's going to stay. So that's the story of localization of light. But before I finish and ask for questions, I just want to talk a little bit about possible experimental realizations. These can be quite tricky in electromagnetism, because particularly for optical systems, you're going to have to modulate with a frequency which is not necessarily the same frequency as the light, but certainly within a factor of 10 or 100 of it to achieve the right velocities that you need. But it turns out there are materials which you can modulate. We have a paper which talks about graphene, and graphene can be modulated very, very rapidly in the gigahertz region of frequencies, and with velocities which can be anything you like. And graphene also supports surface plasmons, and then in the terahertz region. So that the bilayer graphene is one possible system in which you could modulate the system in the way that I suggested. Other systems have been proposed, which, for example, you can make a transmission line, only with the difference now that instead of having a normal capacitor, this capacitor can have its capacitance altered dynamically. It's called a Dirac. And by changing the standing voltage across it, you can vary its capacitance. And this has been proposed as a transmission line model of the effects that I'm talking about. But perhaps even richer is the field of acoustics, where modulation is not really much so much of a problem there, because the frequencies are all much lower. You have piezoelectric systems, and my surprise is that so little attempts have been made in the acoustic field to actually generate these time-dependent systems. So there's an opportunity for some enterprising experimentalists. Not only in acoustics, but also these things have happened in waves on the sea. And one of my favorites here is a story of which appeared in the Times a couple of years ago. Off the seas, in the seas off the coast of New Zealand, they monitor the heights waves there in the Pacific, and one of the boys measured this fantastic rising and falling of 24 meters, the height of Buckingham Palace, and it's tallest wave ever measured down there. But very significantly, they sought to explain this by what was happening was that the typhoon was moving through the region at the same time, and as you know, the typhoon creates an area of low pressure, and that sucks up the sea. That's responsible for these tidal surges that you get when typhoons strike. And so the profile of the sea as the typhoon passes looks like this. And as the typhoon moves, then effectively you have a time-dependent medium with the depth of the sea being modulated by the passage of the typhoon. And in this particular instance, it was known that the typhoon was traveling at approximately the same velocity of the waves. So there you have it, localization of sea waves. And with that, I come to my conclusions. Time-domain metamaterials greatly expand the range of properties which you can get in liminal in metamaterials. So you have access now to bi-anisotropy and bi-anisotropy. Thank you. And that gives you access to a host of problems which have relevance to Berry phases and so on. Most realizations of Berry phases in optical systems have been fairly trivial ones. And to get really interesting ones, you have to introduce something a bit fancier. And these time-dependent systems are capable of doing that. So theorists are presently having a lot of fun and games with these time-dependent modulations. A point worth emphasizing again is that because there's no physical motion, it's realistic to envisage that the phase velocities can get to an exceeding the velocity of light. And furthermore than that, to make a modulation travel at the speed of light, it doesn't have to be modulated at the speed of light. So the velocity of the modulation is the reciprocal lattice vector divided by the frequency of modulation. And so if you have a very long period grating, it doesn't have to be modulated at a very high frequency for the speed to be extremely fast. And an instance of that is a tsunami. So a tsunami has a wavelength of maybe a kilometer, but it races across the ocean at a speed comparable with the speed of sound, several hundred kilometers an hour. And of course, the motion of the sea at any one point is really very slow, but the wave profile itself moves very, very rapidly. And so you don't have to modulate a very high frequency to have a very high velocity. And that's a bit of a let out for the practicalities of the situation. Now, I've been talking about luminal modulation, and this amplifies input fields, even DC fields. And in doing so, because it compresses the fields, the lines of force of the fields into a very, very sharp pulse, you create harmonics. And so this is a way of generating a supercontinuum. And I'd like to point out this is an entirely novel mechanism. The squeezing of the lines of force towards an accumulation point is quite a different mechanism from sticking a wave into a gain medium and watching the number of lines of force increase. Here you work with the same number of lines of force all the time, however great the amplification. And the localization transition occurs when the speed of the grating approaches the speed of light, but there's the two critical velocities, and these critical velocities are the velocity of light at the points of maximum refractive index and minimum refractive index within the scope of the grating. And finally, there are a few papers here which we've written. There are several in preparation. But the ones which are available, the now drag paper is available in Proceedings of the National Academy, and this paper here is available in Physical Letters. So I'll leave that with you, and I will now hand over to Sebastian and call questions. Sebastian, should I leave my screen on there in case people want to refer to the slides?
Yes, please do, Professor Pendry. So I would like now to please ask anyone to come forward with your question. It's a unique opportunity to interact with John Pendry. So raise your hand and unmute your microphone.